One and all to the glorious spectacle that is the RASC Ottawa Centre meeting for August 2024. My name is Mick Wilson, and I unfortunately cannot be there with you in person because of a technical difficulty, namely my bloody Jeep wouldn't start at the last minute. So Zoom comes to the rescue again. So Dave, if you can roll us on, please.
Okay, now the clicker is working.
Okay, yeah, I know what that's like. So, yes, our program for tonight is the normal introduction, notification about this next star party, members in the news and so on. Dave, as usual, will do the skies for August. Our guest coming in for tonight is Robyn Fiori from NRC. She's been a presenter for us a couple of times over the last 4 or 5 years, and it's glad to have her back to talk about the great Aurora of May. We then have John Thompson doing an intro to SeeStar, the one-in-all unit smartscope. We take a break. We then have Tim Yaworski coming in all the way from Saskatchewan to give us a demo, a live demo. He's a very brave man of said SeeStar smartscope. We've got only a couple of observation reports tonight. Richard Taylor will do the monthly challenges as usual, and then the normal closing out material. Thanks, Dave. Next. As usual, we are recording this for posterity, so watch your language. If you need to pose a question, use the Q&A because the raise your hand is not available. Anything you put into the chat box, comments will be seen by everybody everywhere for the rest of history. Next, please. So we have 7 new members joining us this month. I'm not sure whether any of them are in the audience. Can you yell out if you are? I hear nothing. Anyway, welcome. Whoops. And a total of 62 new members for so far this year. It's pretty good. The benefits, the bribes. Why do you want to join Ottawa RASC? Number one bribe is the great people who are standing by to share their experience and expertise, whether that's on technical issues, on the scientific aspects of astronomy, on getting started as an amateur. We've got so many people here to extend a helping hand, as well as top-notch speakers coming in to educate all of us. Physical benefits, you get access to the Ted Bean Loan Library. We've got over 30 telescopes there for you to try before you buy, or if you're thinking of an upgrade to get a feel for what you're taking on with a bigger scope. You get access to our private members observatory, the Fred Lossing Observatory out near Almont, and its regular monthly star parties. Normally, not this month, but normally you would have access to the Stanmont Library out the back, behind the stage of the auditorium there. And as a member, you also get to participate in the RASC's National Certificate Program for gaining observational capability, proving that you can master aspects like lunar photography, astrophotography, and the likes. Next. The print material is the bi-weekly RASC journal. It's a more sort of learned volume that comes out bi-monthly. The annual Observer's Handbook, which will be starting to go out in 2 or 3 months' time for 2025. And our own cheery and delightful local newsletter, Astronauts. Next, please. You get access to the RASC Ottawa Discord server. It's members only, an informal channel for chats and communication and asking questions and the like. Highly recommended. You also get RASC's discounted access to the pro version of Astrospheric, which is a weather forecasting app specifically tailored to the needs of amateur astronomers. And that's like a $60 a year benefit. So next, please. What's all this cost? For a regular membership, a bit over $100 a year. For a family, also near $100 a year, plus per head costs for each adult and each youth. And if you're under 21 years old or a student under 25, then you get membership at $62.40 a year. Next, please. Members in the news, big splash. Andrea's wonderful photo of the May Aurora event made it to the cover of the RASC Journal. And that is an absolutely gorgeous shot and very, very well done, Andrea. Next, other news concerns Australia. We haven't had Australian news for a bit, so move it along, Dave. As you know, for years now, I've been rabbiting on about how fabulous the skies are down under. I've met with much skepticism. I've been poo-pooed. However, you can see here, this is from the ABC News. This is the official government news channel, and you've got a headline there that Australia gets a front row seat to some of the best night skies in the world in winter. So there, it's official. Next. Next star party is next Friday. Oh, sorry, tomorrow. Take that back. Out at the Carp Library parking lot as usual. Last I heard, Katie was still looking for volunteers to help with marshalling of the traffic and parking. She was also looking for more telescopes to be there for showing the skies to our visitors who join us. And August is usually a pretty busy star party. So tomorrow night, Carp Public Library car park next to the Diefenbunker. Next, please. David, back to you.
Okay, folks. I'm sorry. I am here. I'm just sitting up in the booth because Chris is away and Mick is away. So you're going to have to start listening to me virtually here. Apologize for that. So let's take a look at the Ottawa skies for August. And let me just get them to move. There we go. So here are the moon phases for August. August 4th was the new moon. August 19th is the full moon. It is also a blue moon. There's two definitions for a blue moon. The more traditional definition is the third full moon in a season. And sorry, for the fourth full moon in a season. And that is what is happening on August the 19th. The other less formal definition for a blue moon is 2 full moons in a month. So anyways, we do have a blue moon this month on the 19th, and that blue moon is known as the sturgeon moon. Time when you catch sturgeon. It's also known as the corn moon and the green moon. Of course, we have the Perseid meteor showers. They're there right now, but they peak August 12th and 13th, and it's one of the better showers, 60 meters per hour. It was produced by Comet Swift-Tuttle. It was discovered in 1862. The first quarter moon will block out some of the fainter meteors in the early evening, but shortly after midnight, dark skies, be an awesome time to go take a look at them. The days are getting shorter daylight in any case. So you can see the sun rise and set times. Mercury is now visible. It's rising and setting with the sun. Venus is visible in the early evening. By the end of the month, well, right now you'll be able to see it in the evening sky. Mars is visible before sunset. It's gradually moving into the evening sky, and later on in the fall, we'll be able to see Mars in the evening sky. Jupiter is visible before sunrise. Saturn's visible in the evening now. At the start of the month at 10 o'clock, by the end of the month at 8 o'clock. So it'll be great. Uranus is visible in the evening and through the night, as is Neptune. And for the folks at Starfest, this is they're setting up for the meteor shower. And of course, you gotta make sure you're looking the right way. Great. Thank you.
All righty. Thank you, David. So, to our guest presenter, Dr. Robyn Fiori, an expert on all things to do with electrogeomagnetic things pertaining to Earth's atmosphere. She works in the Hazards Information Service of NRC, and she, as I said, has been a presenter here at least twice before and is very much welcome back for her third appearance. So her research is applied to development and improvement of space weather forecasting tools with particular reference to infrastructure impacts on infrastructure impacts arising from CMEs and other solar-related events. So with that, I will pass it over to Dr. Fiori. Thank you.
Oh, perfect. I was just going to ask.
I apologize for folks online who won't be able to see you because the fellow with the projector is online.
Oh, not a problem. It's just the play button, I take it?
The green button, yeah.
Okay. And is this the live mic? Okay. Can I be heard okay online? I'm going to go with yes. So my name's Robyn. I worked with
Absolutely fine, Robyn.
Thank you. I work with Natural Resources Canada in the Canadian Hazards Information Service, and we have a space weather desk there. In the past, we've called ourselves the Canadian Space Weather Forecast Centre, but we go with Canadian Hazards Information Service, or CHIS now, and we're actually part of a larger group that looks at other hazards as well. But today I'm going to talk to you about space weather. So I've just got a couple of slides setting up what space weather is, and then what I really want to focus on is this event that we had in May earlier this year. A little late to be having it, but there were some scheduling difficulties to get it sorted out, but better late than never. So space weather is what we call the processes or the phenomenon that are occurring between the sun and the earth. We're looking at impacts to our geomagnetic field, and we're looking to impacts to our upper atmosphere, or the ionosphere. So the earth is, the sun is continually streaming out particles in the form of what we call the solar wind. This is normally moving at about 400 kilometers per second. Now it's a little bit slower at about 350 kilometers per second. But we also see bursts of activity, and we see a magnetic field being drawn out from the sun as well. We call this the interplanetary magnetic field, or the IMF. And it's the interaction with this magnetic field and with the solar wind particles with the Earth's own magnetic field that causes space weather. And this can have impacts to systems at and near the Earth. So we're very interested in what's going on the sun, because of course the sun is where space weather is originating. We have this normal stream of solar particles, but we can have extra bursts of activity where we have more particles being emitted, higher energy particles being emitted, or we have a higher velocity solar wind speed, our solar wind stream coming towards us. Anything that changes what the normal interaction is between the Earth and the Earth's magnetic field and the sun is going to cause a potential impact. So we can measure the level of the solar activity based on the number of sunspots that we see on the sun. So here's just a close-up image of some sunspots. These are regions on the sun where we have very high magnetic fields. So we have a cooler region on the sun, and this is where we tend to see a lot of activity. This is what we call an active region, where we would see maybe a coronal mass ejection coming out, or a solar flare. So here's a picture of what the solar cycle looks like. So we tend to count the number of sunspots that we see. We average it over a month typically, and this is how those yearly means, this is yearly average of sunspot cycles. This is how that's varied over a longer period of time from 1700 until almost the present day. So you can see that there's a cycle of activity. We have periods of high sunspot number counts. We call this solar maximum, and then the period of low sunspot number counts, or solar minimum. When we have a period of solar maximum, we see a lot of space weather, a lot of eruptions on the sun, and we see a lot of impacts at and near the Earth. And this is what happened in May earlier this year. So just to give you a frame of reference, here you can see 3 different images on the sun. From left to right, we're looking at a sun that's moving from being quiet to being very active. So when the sun's quiet, we don't see very many sunspots. There's just a couple of dots there. But then when we have an active sun, and this example is from 2001, where we had a period of solar maximum, you can see a lot of dark regions on the sun. So these are individual sunspots and groups of sunspots, and they're quite large. So the larger cluster on the upper part of the sun there would be several times the size of the Earth. So these are quite big. In the middle, you can see the sun in kind of an intermediate period. This was from 2023, so not that long ago. We've got a few sunspots, something a little bit interesting starting to go on. And just for reference, this was the sun from the 29th. So that was Monday of last week. So you can see we do have quite a few sunspot groups on the sun. It's certainly more active. It's not as active as it was in 2001, but we're not quite at solar maximum yet. So we'll see what happens. So when we're looking at the sun, we're interested in 3 specific types of phenomenon. The first one would be a solar flare. So this would be a brightening on the sun, usually at one of these active regions where we have the sunspots. And this is a burst of radiation coming from the sun across the electromagnetic spectrum, but we can see it in visible light and very strongly in X-rays. So we call this a solar X-ray flare. And this is something we're interested in because this can have impacts to high frequency communications. Mostly this is having impacts at lower latitudes near the equator. Anywhere the sun is stronger, the sun is brighter, is where you're going to have a bigger impact for this. This is a neat phenomenon because it will reach the Earth within 8 minutes of it erupting. It doesn't have any physical impact to systems. It won't damage a system on the Earth. It'll just make that radio system unusable for the period where the flare is going off. And then as soon as the flare is done, there's no more impact to the system and we can go on using it as normal. So for example, if you're on a boat in the middle of the ocean and you're trying to communicate to shore or to another boat by radio, you might not be able to do that for half an hour, but after that, your communication systems will be fine. The next kind of phenomenon that we look at are coronal holes. So this is the long, dark region on the sun that's going almost all the way across the sun from north to south. This is a region where we have open magnetic field lines. We've got a lot of the solar wind streams coming out from the sun. We can have an additional high-speed stream coming from this coronal hole. And these high-speed streams can be very fast, say more than 1,000 kilometers per second in some cases. And when that extra fast solar wind stream reaches the Earth, it's going to interact with our magnetic field. Those particles are going to make their way down into our upper atmosphere, and we're going to see impacts there. Those particles are also going to flow through satellites that might be orbiting the Earth. We know we have a lot of satellites right now, so we really have to be aware of when we have these very energetic particles. So in 1994, there was a large coronal hole that took up most of the southern hemisphere of the sun that was responsible for knocking out the INIC satellite. And that was very costly. It actually knocked 2 satellites out. One was recovered fairly quickly. The other one wasn't recovered for quite a few months. And then the final phenomenon, and the one that's, I think, the most interesting, is a coronal mass ejection. So this is when we have an explosion of particles from the sun. We're talking about explosions on the order of a small moon. So this is quite a bit of mass that's coming from the sun, a lot of energetic particles, and those are going to hurtle towards the Earth, dragging along a magnetic field. And when that reaches the Earth, we can see impacts as well. Now, if these explosions hurl plasma out at very fast speeds, typically we're seeing explosions that are maybe pushing plasma out at about 500 kilometers per second. We get really interested when those move to 1,000 kilometers per second. Very rarely we'll see 2,000 kilometers per second. We'll see that bulk of plasma reaching the Earth as fast as 12 hours, and then anywhere from maybe 1 to 5 days later, depending on exactly how fast it's moving. The faster it's moving, the more interested we are in it because we're going to see a bigger shock once it reaches our magnetic field. So this is an example of a coronal mass ejection that's moving towards us because, of course, these can explode off in any direction, but we're really interested if they're going to be coming towards us. And you can tell it's coming towards us because of the halo around it. We call that a halo CME. And then the final phenomenon that we look at is a solar particle event. So this is when we have solar energetic protons being released from the sun. Usually this happens at the same time as a solar flare or a coronal mass ejection, and these particles can come towards the Earth. They'll flood our ionosphere and they'll cause problems with radio wave propagation as well. So here's an example where we've got a CME that's erupted from the sun, and just a few hours later, you can see interference with the camera that's imaging the sun right there. Just the snow in the image or the static would be from those solar energetic particles. Now, anytime we have an impact on the Earth, it's because we've had some interaction between our geomagnetic field and the solar magnetic field or the solar particles that are coming. So our magnetic field is basically a force field. It's protecting us from a lot of these particles. It's actually seeded by the sun's own magnetic field. But that force field is distorted as it protects the Earth from these particles. So we've got the sun over on the left side of the screen. We've got particles streaming towards the Earth, and it's distorting our magnetic field from a dipole shape so that it has the shape that you can see on the screen here. It's rounded on the front, and then it stretches out on the backside called the magnetotail. And whenever we have a magnetic field on the sun or from the sun that's pointing in the opposite direction as our geomagnetic field, we're going to have interaction between the magnetic fields. Particles are going to funnel into our magnetic field. We're going to have a lot of energy building up. Those particles are going to make their way down into our ionosphere, and we're going to see the northern lights, which is something that we saw quite a bit of in May of 2024. And it was the interaction between our magnetic field and the solar magnetic field, or the interplanetary magnetic field, I should say, that caused those really spectacular aurora. Now, Canada really has to be aware of space weather because of our location with respect to the North Magnetic Pole. So here you can see an image of Canada, and overlaid on top of that is the auroral oval. This is where energetic particles are precipitating into our ionosphere. So you can see it covers all of Canada. When we have a large space weather event, that auroral oval will actually shift down to lower latitudes and cause impacts to systems below in altitude below that auroral oval. When we move down to lower latitudes, we start to get interested because we have our cities with higher populations there. So for example, March of 1989, there was a large magnetic storm. That auroral oval shifted down so that it was right on top of the Hydro-Quebec power system. That caused currents to be induced in the system, which caused a major province-wide blackout that extended into the States as well. So this is something we have to be aware of. Now, the May 2024 event that we saw earlier this year was very similar to the March 1989 storm. It wasn't quite as strong, but in this event, it was very interesting because the auroral oval expanded so quickly that it actually dropped equatorward or below the southern border of Canada. So we didn't see the strong impacts to the power systems that we saw in the March 1989 event. We're interested in space weather because of the impacts we can see to our different technologies and infrastructure. So the systems that are most vulnerable to space weather are shown here. We have satellites, which are located directly between the sun and the Earth. So they are going to be impacted by energetic particles that are moving through them. That can cause damage. And I gave the INIC satellite as an example there. We also have impacts to our ionosphere, which is the upper region of the atmosphere. You can think of these energetic particles as causing our atmosphere to thicken. When that happens, it's going to impact signals that are traveling through it. So we might have a satellite signal moving through the ionosphere. We might have a signal, for example, passing between a GNSS satellite and a GNSS receiver on the ground, or maybe in your watch. And that's going to interfere with that signal, causing an inaccurate position estimation. So the GNSS satellites, there's quite a few of them to triangulate. I say triangulate with quotations because usually you're not using 3 satellites to triangulate your position. You're using maybe 15 satellites to triangulate your position. You need a minimum of 4 to get a good position estimate. If we have impacts in the ionosphere that are interfering with that signal, it could mean that you are losing lock with some of your satellites, and so you're reducing your accuracy. And that might not be very important to you when you're going for a walk or for a jog, but it might be more important to you for some precision applications like precision agriculture, for example. During the May 2024 event, we did see impacts to GNSS across Canada, across the world actually, mostly in the higher latitude regions. Lots of impacts in Australia, for example, Japan, some impacts in China, across Canada, especially around Gander. We also saw a lot of impacts in the States, and this was reported in the news because the storm happened around a key planting time, and precision agriculture is very widely used to make sure that fields are used as efficiently as possible, and so it wasn't possible to use that infrastructure at the time. Okay, actually, I'll just go back to a couple more effects we can have. One of the main reasons why our office was established was to look at space weather impacts to power systems. Anytime you have a long conductor, like a power system or originally telegraph line, also a pipeline or a submarine cable, you can have currents induced in them. Anytime you have a magnetic field that changes or fluctuates, so for example, when CME plasma or another magnetic field interacts with our magnetic field, we have a fluctuation in our magnetic field, and it can drive currents into some of these different infrastructure, which will have impacts to them. So power systems, of course, are the big one. The March 1989 storm is an example of that. We're also doing a lot of research into impacts in submarine cables as well, railway lines too. And then the final thing I just wanted to mention is the impacts to aviation. Whenever you have these changes to our ionosphere, it's going to affect signals that are propagating not just through them, but that rely on our ionosphere to propagate over long distances. So high frequency communication, this is something, for example, that you might use in your ham radio. It's used by aviation, it's used by the Maritimes for communication as well. You're going to have a signal that will bounce off of the ionosphere, allowing it to travel over very long distances. This was really important, for example, in the Second World War, when we were looking at communicating with submarines and communicating with vessels off the coast. So whenever you have a thickening of the ionosphere, it influences that signal, so it may no longer propagate. So if that happens, you have to look at other methods of communication if they're even available. So I told you earlier that a solar flare can have impacts to high frequency communication. And this is actually something that happened in September of 2017. I'm not sure if you remember, but September 2017, there were a lot of natural hazards going on. There were hurricanes occurring at lower latitudes. There was also a major earthquake in Mexico. And those rescue efforts for those both events were actually influenced by some major solar flares that were going on at the same time. In such cases, in the Caribbean, there were instances where emergency response messages weren't getting through to people to tell them to shelter, for example. Okay, so that's kind of a quick overview of space weather, and I'd be happy to answer questions in the break, or if you have questions later. But what I'd really like to do is to show you some examples of data coming from this event we had in May, because it was really quite fascinating, because the event really shouldn't have happened, to be totally, completely honest. Here we have just a snapshot or a close-up of the solar cycle from 2014 through to 2024, early 2024. So you can see that right now we're moving into a period of solar maximum. We're moving up that curve. That peak is supposed to happen somewhere around 2025. So we're expecting to see 2 or 3 more years of high solar activity. And you can see that the solar cycle that we're in right now is maybe just a little bit higher than the solar cycle that we saw previously. Now, I will say that this last solar cycle was very small compared to previous solar cycles. So we're still looking at a baby cycle right now. And this is probably a good thing, because right now we're also moving into a period where we're very, very reliant on technologies that are impacted by space weather. So it's important for us to get a feel for what can happen to these technologies, and what kind of size of events should we be looking at. One of the things we're really interested in our office, for example, is what is the extreme event? What's the 1 in 100 year event, so that we can protect our systems against that? But not even worrying about that 1 in 100 year event. more practically, what's the 1-in-1 solar cycle event that you're more likely to have to deal with? And the event that we saw in May 2024 was one of those events. Actually, we would call it about a 1 in 40 year event. If the March 1989 storm that caused our power blackout was a 1 in 60 year event, this one was a little bit smaller, about a 1 in 40 year event. So here we have the sun, and I've circled in red the active region that was responsible for this. So this active region was numbered 3664. I was the space weather duty forecaster the week before this event happened. I was really mad because at about 2 in the morning, every night for about 5 nights, we had an X-class solar X-ray flare. And an X-class flare is the criteria threshold for calling me to let me know that an event's gone on so I can see what's going on the sun and what other kind of activities happening. In the middle of the night, we don't see impacts from solar X-ray flares, but people in other parts of the world do, so we have to be careful of that, and there can be associated phenomenon. So I was pretty mad at this active region, but 2 days before I handed, 2 days after I handed over my shift to the next duty forecaster, we had some pretty major activity. So the active region crossed the central meridian on May 7th. Over the entire period that it was facing the Earth or visible on the solar disk, it was emitting 1 to 2 X-ray flares of the X class per day. Now I'll show you an image in just a moment of how the solar X-ray flux was changing. But like I said before, most of those large flares were happening while Canada was on the night side. So we weren't seeing direct impacts, but we were hearing about impacts from some of our partner communities. I think my video is going to start. I'm not sure how to work it here. Let's try again. Okay, so our active region is just starting to rotate around the sun now. It's just crossing the central solar disk, and you can see that it's growing in size. So our sunspots are darkening. We're seeing a lot of activity. Let's watch that come around just one more time. Oh, we'll go back. Sorry about that. Okay, we won't go back. Technical difficulties on my end here. We're going to watch the same region on the sun. You're going to see it on the lower portion of the sun in the southern hemisphere. It's going to come from the left of your screen, and it's going to rotate around to the right, and you're going to watch the solar flares erupting from the sun. You're going to see little bright flashes on the sun. So our active region is coming around now. You can kind of see little flickers going on. Those are solar flares. There's a bigger one there. That was a big one right there. That was probably one of the bigger ones. And then we're going to see another one just now as it rotates off the side. Each of those big flares was accompanied by a coronal mass ejection. And the one that erupted while it was at the center of the sun was pretty sizable. That was the center of the solar disk, I should say. So right now you're looking at a graph of solar X-ray flux. On the bottom axis, you're seeing dates from May 7th through to May 14th. And if you look at the orange or upper line, you can see a lot of fluctuations. And anytime we have a peak in that X-ray flux is when we have a solar X-ray flare. So I've highlighted those with arrows. You can see around the middle of the plot, on May 10th and May 11th, we had a couple of very large X-class flares. But if you look on May 7th and May 8th and May 9th, there are 4 arrows on May 7th and May 8th, and then another 2 arrows on May 9th. And these were M-class flares that had coronal mass ejections associated with them. And these were ejected around when that active region was pointing directly towards us. Now, another really interesting thing to notice is that the background level of the solar X-ray flux is quite high. If you look on the right, you can see letters A, B, C, M, and X. That orange line, or the baseline of the orange curve that you're seeing, is at about an M-class flare level. Usually that baseline is down around a C-class flare level, so it's quite large. And this isn't something we see very often, although it's something that's happening right now too. So here's another plot that I put together for you. What it's showing you is the number of X-ray flares that have erupted yearly since 1980. And the very last point, you can see the orange line moving across it, shows the number of flares that have, of X-class flares that have erupted so far this year. We haven't seen that level of X-class solar flares in 33 years since 1989. You can see that we had about 60 yearly flares in 1989. So this is a very active sun right now. So here you can see a couple of images of the coronal mass ejections that were of particular interest to us. So we saw a series of about 5 coronal mass ejections between May 8th and May 10th. And these all arrived at the Earth around the same time. So individually, none of these flares were really, or none of these CMEs were really interesting, except that they occurred while the sun was, or while the active region was facing the sun. So if you look at the CMEs on the blue images, you can see kind of a light shadow around the sun, and that's the coronal mass ejection. If we have a strong coronal mass ejection, we tend to see a really bright, high contrast in the images. These CMEs, none of them on their own was very interesting. But the interesting fact, and the reason why the Space Weather Prediction Center in the United States kind of blew the trigger on alerting people for this event, was that they were all set to arrive at about the same time. The CMEs were set to piggyback on each other, and we call those cannibal CMEs. They ate one another to make kind of a big CME. And I've actually got a video of that one of my colleagues put together. So I'm going to play the video for you. We're looking at the sun and the Earth from above, and you're looking at the solar wind stream that normally comes out from the sun. And you're going to see each of the individual CMEs erupting from the sun and reach the Earth. And what I want you to notice is how the CMEs kind of collapse together. And the other thing I want you to notice is that we're not receiving the bulk of the plasma. The solar wind was rotating in such a way that we just get the tail end of it. So go ahead and watch that now. So we're on the 8th, we see our 3 CMEs and then 2 large ones and a couple of extra ones coming through as well. So I try playing it again for you. Maybe if I go back a couple of slides. There we go. One more time. So we're just getting the tail end of that plasma. Now, the fact that we're getting the tail end of that plasma cloud isn't important because the CME is less strong on the tail end opposed to the central part of it. It's the fact that we see that bulk of that plasma cloud for a smaller period of time. So we were only exposed to the plasma cloud from that series of coronal mass ejections for about a day, when we could have been exposed to it for a much longer period of time had those CMEs erupted 2 or 3 days earlier. So a lot of space weather is about timing and being in the right place or maybe the wrong place at the right time. So here we see our CMEs arriving. So I'll just explain this diagram a little bit. We're looking at a time series plot from May 10 to May 12, and we're looking at the characters of the solar wind and the interplanetary magnetic field. So I'm going to point out 2 plots for you. Thank you. The upper plot, the very top one, is the magnetic field from the sun. We're interested in whether or not the magnetic field is pointing up or if it's pointing down. If it's pointing up, it's pointing in the same direction as our magnetic field, and we're not going to see a lot of impact. But if that interplanetary magnetic field is pointing down or negative, we're going to see those magnetic field lines joining together. They're going to connect, and we're going to see a lot of impact between that plasma cloud and the Earth's magnetic field. And that's exactly what happened here. So if you look at the top plot, do we have a pointer? If you look at the top plot, the red line shows that direction of the magnetic field, and it goes down. So we see a very negative magnetic field. And you'll see that that magnetic field was negative at almost minus 50 nanoteslas for over a day. Usually the magnetic field fluctuates between plus or minus 5. So being negative at minus 50 for over a day was almost unheard of. So the fact that these CMEs erupted when they were facing the Earth, the fact that these CMEs multiplied on each other, that wasn't actually the driving factor between this big storm. It was the fact that the interplanetary magnetic field was so negative for such a long period of time. So if these had arrived at the Earth with plus 50 nanoteslas, we probably wouldn't have seen anything. So it was really quite interesting. And what makes it more interesting is that when the US notified the media of this event, which caused quite a bit of media spread across the world, they didn't know what direction that magnetic field was going to be pointing in. So we don't actually have a picture of this until that plasma cloud reaches a satellite that's located about 30 to 60 minutes upstream of the Earth. So it was a very, very good example of how their models work. The other thing I want you to look at is the speed of the solar wind that's coming towards the Earth. And I just want to show you that we had a slow solar wind speed of about 400 kilometers per second. And you see the sudden jump up to 700 kilometers per second. That's just the shock. That's the indication that that first CME arrived. And then you don't really see clear shocks when the rest of the CMEs arrived because they were piggybacking on top of each other, essentially. Okay, so if we go to the next slide. There we go. In addition to a magnetic field coming towards the Earth, we saw a lot of particles coming towards the Earth. We had an energetic proton event at the same time. So we've got, this is just a plot of the protons. You can see that they're at a small level, and then we see some enhancements. Now, this level of enhancement isn't really all that significant, but what's interesting is that we had a solar particle event, and we had a geomagnetic event. So we had ionospheric disturbances and we had magnetic disturbances. Every single system that could be impacted was impacted in some way because of this event. Okay. When we have those particles arriving towards the Earth, what they do is they thicken our ionosphere and they cause absorption of radio waves. So we don't see good radio wave propagation. So here's just a map showing where that enhancement happened over Canada. The darker the map is, the more absorption. So most of the impacts were observed here, which is where NAV Canada reported a lot of impacts to communication. So we definitely saw this. We also heard about impacts to communication with Australia, Japan, and China as well. Also South Africa, across the Antarctic and across the Arctic. Some planes were rerouted to try and avoid these regions where communication would be impacted. And that has a very large consequence because there's a cost associated with rerouting a flight. Often you have to change how much luggage you can carry, how many passengers you can carry. And then there's a cascading effect, of course, if connecting flights are impacted too. So that's something the aviation industry is very aware of and very concerned with when it comes to space weather. We also saw a phenomenon that we call scintillation. And what that really is telling us that there could be a potential loss of lock between a GNSS satellite and a GNSS receiver. And we observed that this map is for May 10th and May 11th. And we had, what you really need to see is just these lines. We had a low level of scintillation and then a sudden enhancement. And then a lot of fluctuations. And we did have a lot of reports of impacts to GNSS throughout this event as well. So in terms of the Canadian space weather forecasting from the Canadian Hazards Information Service, what do? We do monitor these. We get alerts when certain thresholds are crossed for activity, thresholds on the sun. So when we have a solar X-ray flare, for example, when we have a solar proton event being observed, we also have thresholds in our geomagnetic activity. And in terms of geomagnetic activity, we saw enhancements from the evening of May 10th. Actually, we saw enhancements beginning midday on May 10th. All the way through to May 13th. So we issued a major geomagnetic storm watch. So this is like a weather watch. It means we're expecting enhancements in activity. We issued that quite quickly as soon as the event arrived through to the 13th. And then we issued a major geomagnetic storm warning across Canada and then just isolated to the auroral zones at the start and the end of that event. And that indicates that we were actually observing enhancements in the magnetic activity. So we were seeing a lot of fluctuations in our activity. They were crossing thresholds where we might expect to see impacts to things like power systems. But like I said earlier, in this particular event, because that we had such a shock when the event arrived, the auroral oval basically shuffled down past the infrastructure that we have in Canada. And it caused a smaller impact in Canada than could have happened if that hadn't been the case. We also issued a warning for solar protons because of our solar proton event from the 10th through the 12th. This particular active region actually issued another large coronal mass ejection just as it was rotating off the visible disk. And although the coronal mass ejection from that didn't reach us, the energetic protons, which kind of curve around as the sun is turning, did reach us, and we had a stronger solar proton event just a few days later. And then the last slide I just wanted to share with you, of course, is just one of the nicer consequences of this is that we do see the aurora. The show in Ottawa was a little bit harder to catch because there was cloud cover that day, but some beautiful pictures. These are coming from the Olympic Peninsula. I'm not sure where that is. Sorry, my signs have gone down. This particular picture here is from one of our duty forecasters who lives in Embrun. And then this one's from Saskatoon. So that's the event for May 2024. I did have some questions about how we look at this event. So we do have in Canada a series of duty forecasters that are on call 24/7. So we respond to system alerts from observations being analyzed through our system. We're working actively 8 hours a day and then on call 24/7 the rest of the day. Our poor duty forecaster on call during this event was pretty exhausted by the end of it, so much so that he had to change the ringtone on his phone because it was causing problems for him. But we actually were all on call for this event. It was pretty exciting. We had 5 duty forecasters working actively on May 10th, monitoring different systems. In addition to being on call within Canada, we were also acting as a global warning center for a service to International Civil Aviation Organization. And then we had 1 duty forecaster, actually me, in this case, who was just responding to calls from the media. And then that activity went through on Saturday, and we had 2 forecasters active that day with additional support for the media. And then we were able to drop down on Sunday to just 1 duty forecaster. So this was a really exciting kind of once in a career type event, although I am hoping against hope that it's not just once in a career. I'm happy to answer questions. If you need to move on, I can stick around during the break too, of course.
Robyn, thank you so much. It's always a pleasure to hear you speak.
Hang on a second, folks. I'm just going to bring a microphone down so folks online can hear the questions.
I've got a microphone here. Is that live?
Yeah, just turn it on. Oops.
Okay. Are we good, Dave?
Okay, so hang on. I got a question up here.
Nah.
What is the makeup of the charged particles coming from the sun? Is it just protons? And during a coronal mass ejection, would the makeup of the charged particles change?
We see energetic electrons and energetic protons. So when we have a coronal mass ejection, what happens is the solar protons are actually accelerated on the shock front, and they'll arrive at the Earth within maybe 1 to 3 hours. So when we have a flare, one of the first things we do is we watch the solar protons to see if they rise, because that's an indicator as to whether or not something else is coming towards us. And then the solar energetic electrons will arrive later with the bulk of the CME plasma cloud. And that bulk is what comes about 1 to 3 days later. And it's those energetic electrons that lead to the aurora. The energetic protons will cause impacts in the ionosphere, but they're invisible.
We've heard that the Earth's magnetic field is changing with time. It may, in some unknown number of years, change direction altogether. How will that have an effect on auroras?
Yeah, that's really interesting. We get a lot of questions about that. So our magnetic field, my lab actually used to be paleomagnetism they looked at. So they looked at cores from the Earth, and they looked at how the magnetic field changed. And the magnetic field actually changes about every 300,000 years. And the last time it was oriented in the opposite direction was about 750,000 years ago. So a lot of people think that we're due for a change, and we're starting to see that right now. So it takes, on the order of hundreds to thousands of years for the magnetic field to actually change. There's been no case in history where it's disappeared, at least nothing that we've measured that would cause our atmosphere to be stripped away. But you're right, there's that in-between period where the magnetic field can become weakened. The magnetic field could actually change so that it's not a dipole anymore. We could have multiple poles on the Earth as well. And it's the orientation and the location of those poles that will affect where the aurora is. So if we were to have multiple poles and we no longer had our dipole axis where it is, it could be that the auroral oval moves away from Canada, or moves to other regions, and we could have more than 2 auroral ovals, which could be pretty interesting. I don't think we'd see that though, unfortunately, because it takes so long.
Do we have anyone else there, Dave?
I'm curious about the origin of the data that is used, all the sensors and things that you are using to make all these forecasts and to track the event as it's going on. Where's all that data come from?
Sure. So Canada itself doesn't operate any satellites, but we do have our geomagnetic observatories. We have 13 stations across Canada to measure the magnetic field. We also have stations called rheometers that measure the thickness of the ionosphere. That's looking at absorption. And then we're in the process of installing some GNSS receivers as well to look at that. In terms of the sun, we're relying on satellites that are being operated by other centers. So we can look at images from the sun from the Solar Dynamic Observatory and Solar Heliophysic Observatory. For particle magnitudes, so protons and electrons and X-rays, we're using a series of satellites called GOES. So these are operated by NOAA in the States. It's a terrestrial weather satellite, but they also have sensors that are looking at proton flux and electron flux and X-ray flux as well. And then the state's SWIPC also operates another satellite. It was called ACE, now it's called Discover, and that's located at the L1 point. So the point where the satellite is basically stationary. It's about 30 to 60 minutes upstream from the Earth in terms of how fast the solar wind moves. So that's when we get our first picture of the orientation of the magnetic field and how fast that plasma is moving. So a number of satellites being operated by mostly the state, but also international groups as well, and then our own ground networks. This L1 satellite that we rely on to get that first picture is really important and quite vital, and it's been identified that that needs to be replaced because it is, of course, running out. The ACE satellite was replaced a few years ago with this Discover satellite, but it doesn't have the same suite of instruments because it was put up relatively quickly in terms of how fast it takes to get satellites going. But there are international efforts to try and replace that, and then to put satellites in other stable positions around the sun so that we can get a better picture of the directionality of some of these events. Yeah, space weather is very much an international effort.
I got a comment and a question. First comment, what a wonderful talk.
Well, thank you.
It was masterful. It was really at the right level for amateur astronomers. Talking of amateur astronomers, I think many of them are aware of the Carrington event.
Yep.
And if I understand correctly, by looking at similar sized stars to our sun, one can get an idea that Carrington wasn't actually that big after all. So here's my question. How bad could it get?
Now, that's an interesting question. We are always worried about the 1 in 100 year event, and we usually scale that to the Carrington event. So we typically treat that as the worst case scenario. And I will say that the Carrington event happened in 1869, but it actually happened again in July of 2012. But that particular case, the sun was not, the ejection didn't come towards the Earth. It ejected off the backside of the sun. And I was on duty for that particular event. And I remember looking at the measurements and thinking, wow, that's a spike. That's ridiculous. I've never seen anything move that fast. And then a lot of people started jumping on it and looking at it. And it actually fueled a lot of research across the globe into space weather, because if that event had happened 2 weeks earlier, it would have been facing us directly. And there's a lot of talk about what the impacts of a Carrington level event would be. And it could be quite catastrophic. And that's why we study it. Without any kind of research and without any kind of mitigation, that kind of event could take out power systems across the globe. So we study that, and we work together to make sure that we know when to turn our systems off, when we need to rely on other power sources, and to make our systems more robust. Make sure we have backups of sensitive pieces of equipment. So that kind of catastrophic event doesn't have that kind of impact on us. Because the best thing about space weather is it happens and then it's over. And if you just turn your equipment off while it's going on, you're not going to have any damage. So there's a lot of things we can do to mitigate against these.
Okay.
Any other questions? No, any online, Mick?
None that I can see, Dave. So I would again like to thank Robyn. As Simon said, fabulous talk, and very much looking forward to having you all back. Well, next time there's a fabulous set of Aurora. How's that?
Thank you for having me. I hope it's soon.
Yeah, all of us do. Okay, again, thank you. Alrighty. Dave, can we move on to John's talk?
Yeah, I just have to run back up to the booth. Is John here? Okay. I'm going to have you come up to the booth where we use the camera and my laptop. How's that? And then everybody down here can see it. And just give us a minute to set this up. So we apologize to the folks online. Mick had some technical difficulties. He's the guy with the camera. So that's why you're not seeing the speakers. And we're going to resort to my laptop camera here up in the booth so we can see this amazing SeeStar instrument.
Thank you for blaming me, Dave.
Should start off that I submitted a couple of these slides, I think it was for the June meeting, and then Mick decided to bump them to the August meeting because there was another talk on the SeeStar, and I guess they wanted to coordinate them. Just as a background, the SeeStar is not the first smart telescope to come out. They've been around for a couple of years now. There's the Veronis and the Dwarf 2 and a couple other ones, but most of them are quite expensive, like $2,000 US and up. But SeeStar was made by one of the more well-known manufacturers, ZWO from China, and they've already done a lot of background in astrophotography. So they weren't the first to hit the market, but they took their time and maybe waited 8 or 9 months after some of the other leaders came in. But they basically used that time to do it right. Everything is just so well integrated and works together so well that there are very few complaints about it. They came out, the first prototype was seen at NEAF 2023, and they actually hit the market in October 2023. And at the time, there was a $100 introductory discount. It was $399 US. And several of my friends, astronomy friends from going way back, jumped on it and immediately bought one. I'm not normally a first adopter of high technology devices like this, and I decided to wait and see what they were able to do with it. And one of them, actually 2 of them, were high-end astrophotographers who really do some really advanced work. So it was surprising to see that they were going to go to a smartscope like this, which has the device do most of the work for you. But anyways, they were trying it out and they were just raving about it. Most of them were using M42, the Orion Nebula, for first light. And when I saw what they were doing, after 6 months of sitting on the fence, I decided to pull the trigger in April. So I called up Canada Telescopes, and it arrived on my front steps 24 hours later. And what I got was this brown shipping container that you see. When I opened that up, there was another, I guess you would call it the shelf box. Here, I'll just get it here. Here.
If I stop sharing, I'll be able to see a bigger screen. Can you stop sharing for a second here? There you go. So now.
Oh, okay. When I opened up the corrugated box, we got this thing, which was a nice sort of box you'd see on the shelf. But surprisingly, unlike a lot of competitors, they don't have all sorts of brightly colored pictures of the things that you'll be able to see. Maybe they were trying to reduce expectations or something, but they didn't really need to. So when I'll open this box, there was the main container, which I'll just do here now. There was no styrofoam in the box, but the case itself is a very thick, high density polyurethane container. So it provides lots of shock resistance if you happen to bump it or drop it. So. So, I don't know if you can, okay. So here it is. What's the contents? It's actually not a lot here, but it's all, again, very well packaged. I think there was a plastic bag around it to prevent humidity as well from getting in. But what there is, first of all, there's the main unit, which is about maybe 10 by 4 by 4, something like that, inches. And it fits on. And then the next item is this little tripod, very short, but again, it's well made. I believe it's carbon fiber legs and everything. When you extend the legs, they're maybe, 18 inches or so. It is workable, but I found in practice that it's better to use a higher tripod. So I'm using
I'll get it for you.
I actually use this longer photographic tripod that I can just unscrew the ball head, and it has. Oh, it's not coming off. And anyways, there's a 3/8 inch threaded stud on the top of it, which fits nicely into the base of the SeeStar. And it gives, so when it's on this, it's elevated to maybe 3 feet high, which is actually preferable because this little one, if there's people around, it's almost asking to be somebody come around and kick it over, especially if you have a really dark site. The thing is almost invisible because everything is pitch black the way it's been made. And there's just a few other little things. There's the quick start guide. There was another guide like this, which is called safety precautions, but it's legal boilerplate, so I tossed it out. The cord is used for both charging the device and also for transferring data to a computer. And the last real thing, accessory was a solar filter. It's a polymer, but it does a very good job. It just slides into the front of the SeeStar before doing any solar observing. So I maybe go on with the slides here.
Okay, so just give me a second here. I'll give you the mic. Just have to find my mouse. Go.
Oh, how do I move them?
Oh, just roll the mouse.
Okay.
Just roll the mouse. I can do it for you. Next slide. Right there.
Oh, okay. Well, there was a slide before that. It's just
Got this one.
there's that one. Now it's set up on the photographic tripod. The tripod that comes with it is only about half that height. Now, this was an interesting slide. I copied this off of a video talking about the uses, and they're comparing this with a typical astrophoto rig. And you can see all the list of things and the equivalent prices. The optics themselves are sort of like Williams Red Cat. It's a 2-inch f5 Apo optical system. And there's a sensor, which would be another like a ZWO camera. There's an autofocuser, there's a filter wheel, there's a dual band, narrow band filter, which is H alpha and oxygen 3. Then there's the mount, well, which is actually built into part of the device. And then there's a computer built right inside the device itself. And then there's a tripod, this rugged carrying case. They have miscellaneous. One thing they don't mention is, well, they don't mention the solar filter, I don't think, do they? And they don't mention that there's a built-in dew heater that you can turn on and off in damp conditions to prevent your optics from dewing up. And then they don't mention that there's all sorts of high-powered software built into it. I'm not talking about the app itself that you have to download onto a smartphone or a tablet. But this is basically image processing software that operates on the fly in real time. Thing is quite lightweight, no wires. And then this is the real kicker, that compared to the setup you see on the right, you see the two of them, it's $2,300 worth. And I think it's actually more than that versus 500. And I've been told I've seen it for $450 maybe. So perhaps the price is coming down. The next one. And again, just comparing the little SeeStar on the ground compared to all these other more massive rigs. And surprisingly, its performance fares very well compared to these other much more advanced setups. Okay, next. Okay, here's some of the pictures I took. I took this one. I had it set up during International Astronomy Day at the Chapters Mall, and that was one of the first. I think it was actually the third time I had it out, so there was still a bit of time, bit of a learning curve. I've seen better pictures than that, but that was my first attempt anyway. And the reason I took that picture was right about just above center in the Sea of Tranquility. There is the Tranquility base where Apollo 11 landed. And I was pointing that out to people at the Astronomy Day feature. There's the next, that is the AR3664 group that caused the massive auroras a few days later. That was on a Wednesday, I think. By Friday, it had rotated over to the right-hand limb, and about 6 hours later is when the auroras actually took off. And there is possible you can blow that up. There is a 1, 2, and 4x magnification built in to the app that you can move things higher. Yeah, that's one thing I was going to comment on. Normally, our pictures that you see in astrophotography are in portrait mode, or sorry, landscape mode. I've got a feeling that maybe SeeStar was appealing to the crowd that grew up on Instagram and TikTok maybe when they decided to make it into a portrait mode instead. But if you don't like that, you can certainly do some cropping and cut off the top and bottom. And sometimes, some cases, it's actually necessary to do that. If you have a longer exposure, you start seeing some field rotation because of the alt-azimuth mount, and you sometimes have to crop the top and bottom to get rid of those field rotation effects. Okay, next. Okay, this again came from that video. It's just showing that despite it being aimed at the general public, it's possible to do some real science with these things. This is something I'd like to get into myself eventually, but I see there are other YouTube videos that talk about it. But here's somebody who's doing the light curve of
Dave, we've lost sound.
Mike has died. Hang on a second.
Okay.
Oh, okay. Well, yeah, that this video was demonstrating that some real science can be done using the SeeStar, even though it wasn't really aimed at that target market. That somebody here made a light curve of an asteroid and then used other software to actually derive what they might think might be the actual shape of the asteroid. Okay, next. Oops, I guess that's it. Oh, yeah, because I submitted a few other images that I took just 2 nights ago.
John, John, you're back on during the observation reports.
Oh, okay.
And
okay,
that,
that's how this goes. All right. Okay,
and that includes the shots you have showing the steps of magnification available and so on.
Yeah, okay. So I guess that's it then until the observations.
All righty, John, thank you very, very much. It's great to see some real-time hands-on astronomy nerding going on. So we're up to our break. Oh, sorry, were there any questions for John? Okay, I'll take that as a no. So we're up to break. The museum's closed, etc., etc. Your break question, even proper astronomers like us are aware of the zodiac, as in horoscopes. How many constellations lie along the ecliptic, i.e. the sun's path through the zodiac? Something to ponder, and we'll be back in...
Total eclipse of the sun in Canada. So keep yourself healthy for the next 20 years. Okay. And I have a feeling it's going to be a really popular star party that year. Okay. So let's get started here. What I've been asked to talk about is the SeeStar. Now, what I'd like to start off with is when I first heard about the SeeStar, I sort of saw this as really an interesting toy, but I really didn't necessarily see the value of it until I got my hands on one and realized that there was a lot more to it than just being a toy. And as well as that, I saw a really great potential use for that, which I'm going to come up with sort of at the end here. Now, some of the information I'm going to be giving you is a bit of a repetition of what you heard, so I'm going to go through it a little bit more quickly. Some of the information is a little more from a Canadian aspect as composed to an American aspect of it. So let me just flip over and let's get started. Okay, so first off, I refer to this essentially as the iPhone of astrophotography. And what I mean by that is when the iPhone came out, one of the real sort of the groundbreaking smartphones, more people started taking photographs. And suddenly we live in a world where way more people are taking photographs than historically ever have in the past because of the convenience and the simplicity of it. And that is sort of the beauty of the SeeStar, is it's opening up the hobby of astrophotography to people who've never even looked up at a night sky. Okay. So let's say you're a person who's interested in trying out deep sky, lunar, and solar imaging. So what do you need to get started? Okay, so as we already heard, there's a lot of tools you need to get going in here. You need yourself a good telescope. You need a good go-to mount. You need a camera, a nice basic camera. Auto-focusing, of course, because you don't want to be focusing. You need a little computer to be able to control all those things and send the information to a tablet. But also, you want a light pollution filter for if you're shooting from your backyard in the city. But you also want a dew heater to make sure that on those damp and humid nights, you're not going to have anything fog up on you. And of course, you want to do solar, you're going to add a filter to it. So all of these are Canadian prices. you're basically getting started in astrophotography for $3,200. Or you buy a SeeStar, which right now is selling in and around, there's some good sales on right now, $640 Canadian for literally every piece of equipment that I just mentioned there is in that nice little box. Now, what's the big difference between the two? Okay, so this is a typical rig. This is my main imaging rig here. And the thing about this is, first off, it takes me about 45 minutes to put it together and then start polar aligning. And if the stars align, so to speak, usually within about 50 to 55 minutes, I'm starting to image. Now, this particular day was in a beautiful lake in northern Saskatchewan. That's not bad. But sometimes in Saskatchewan, it's -30 or -35. And I'm spending 45 minutes in -30 when I want to do imaging. It can really get a little bit colder. Now, a SeeStar, start to finish, basically from powering it up to walking away while it's shooting images, for the most part, takes me about 3 to 5 minutes. So if you imagine being outdoors in -30 for 5 minutes and then spending the rest of the time with the tablet in the house, watching Netflix with your wife and keeping an eye on what the SeeStar is doing, that's a substantial difference between the two. Now, of course, after you've taken those images, you're going to want to spend some time with them. And for the person who's getting started in astrophotography, they're usually going to be using something like Photoshop or Lightroom, or using the software that ZWO includes with the device itself. So that's sort of the basic software most people will start with. Now, what kind of imaging can you expect? Okay, so here's these two rigs side by side. And let's talk about the most popular thing that people shoot in the winter, the Orion Nebula. And this is an example of the Orion Nebula taken with my 6-inch reflector. And that's probably, if I'm remembering correctly, about 2 hours worth of data put into that particular image. And there's a lot of detail in there, and could be much better detail as well if I was a better processor. But the same amount of time on the ZWO, on the SeeStar, you're not seeing a lot of the nuances that you're seeing, obviously, in the much more expensive rig. Now, this is just utilizing the software that it came with and doing a little bit of tweaking in Photoshop. Now, I'll be the first person to say I've seen amazing images from the SeeStar where people have been taking it into software like PixInsight. And PixInsight, in the hands of a person who knows what they're doing, can create some absolutely amazing images with all types of data, even the type of data you're getting from a SeeStar. But not everyone who's starting in astrophotography is going to be spending the money on PixInsight and spending the time to learn it. Okay. But of course, I look at something like that, and if you look at that image there, knowing what the scope on the left can do, you're saying that's a good shot, but it's not a great shot. But put yourself in the shoes of the person who's never done astrophotography before, and they've literally unboxed it and went out one winter night and pointed at the Orion Nebula, and they get a shot like this. You'd be impressed with that. Now, think what I think back of myself when I first got into astrophotography. This was my first shot of the Orion Nebula, and I look at that today and I laugh. But 8 years ago when I took that shot, it was the best photograph I've seen in the world, because I took it with my camera and a 300mm telephoto lens. So you can see why people are getting excited by something like the SeeStar with having no experience whatsoever and getting some amazing images. Now, the other thing about it is it's not always good for everything. Okay, so for example, if you look at the Pleiades, in this case, about 60 minutes worth of, just 60 minutes worth of data taken with my reflector pulls up a lot of the nebulosity and a lot of the details in there. But you do the same thing with the SeeStar, and it's not nearly as impressive. And the other thing about it, and it might be hard to tell in here, you'll notice the image on the left is a square image, because That's the sensor that's on my camera. And the SeeStar, because it is using that heavy duty landscape or heavy duty portrait vertical type shot, I had to find a time when the Pleiades was tilted to fit more of it in the frame. And even then, not all of the stars of it, not all of the sisters are visible in there. But you're not seeing nearly as much of the nebulosity. I find it works a lot better with the emission nebulas as opposed to something like that. Now, solar imaging, this is where it really sort of comes into its own. And as was already said, it comes with that solar filter. And this is an example of just a single frame image taken of the sun. And that's the framing. The only cropping I did here essentially was just cropped it into a square shot. But that's at the 1x magnification, essentially. That's what you're seeing out of the sensor. And as was mentioned earlier, there is a 2x and a 4x magnification where you can get in closer, but that's a digital magnification. So the more you turn that on, the more digital noise you're going to have. So I don't usually use that very often. But a single exposure will pick up if there's sunspots there, pick up some interesting ones. But the beauty of this is it has the ability to be able to do stacking within the device itself. So instead of shooting a single image, I'll turn on the video feature, turn it into RAW, shoot a 15-second RAW video, and then using the software built into the device, then stack that image into an image with far greater detail, especially in the areas around the sunspot. But of course, if you happen to be lucky enough to experience a solar eclipse, this is an amazing little tool for the eclipse. And this is just a brief video that I put together from April the 8th. I was in the eastern townships of Quebec. I based myself in Ottawa so I could go either direction and chase the clear skies. And this is the eclipse start to finish. And literally, for the most part, the SeeStar was completely walk away from it. The only time I had to make any adjustments was when I pulled the filter off during totality. But I was able to get, without having to make any adjustments at all on the framing and the tracking, it kept the sun completely in the frame the entire time. And then I was able to, from that video that essentially a time-lapse video that I shot, I was able to take those individual images and be able to create that that sequence of the eclipse, including things like the corona and the diamond ring. So the SeeStar was a real lifesaver for me for the total eclipse. Now, if we talk about lunar imaging, it's great for lunar imaging as well. If you're looking at thin crescent moon, if you want to capture that thin crescent moon, great. But if you want to get some details in the earth shine, then just crank the gain up. Yeah, you'll blow out the part that's lit by the sun, but you'll be able to pull up some of those details in the earth shine. And same thing, using that stacking, not just taking a single image, but shooting a video and then stacking from the video. Same idea. Here's a single image of that first quarter moon, and there's a stacked version of that moon. And you can see a real difference in the definition and in the detail that you're getting between those two images. As well as in those particular images, I was even able to capture that particular night was lunar X and lunar Y showing up on the meridian, on the terminator. And I don't know how well it's showing up on your screens here, but I was able to capture it that particular evening. Now, there is a solar system imaging setting on it if you want to shoot the planets, but I'll be the first person to say it really is not great for solar system imaging, mainly because it just doesn't have the magnification. This is an uncropped image of Jupiter. This is an uncropped image of Saturn. And you can, yeah, if you want to zoom in and do some cropping and get in closer, you can, but it's going to pixelate like crazy. So I generally don't use it for solar system imaging unless it's something like, for example, a comet. It works really well for comets, and it makes it very easy to find comets as well. But where I find it really shines and this is where I find I get my most use out of it, is in public outreach. Now, I do a lot of public outreach in the area, and a lot of that involves bringing out a telescope to public events and giving people a chance to see something that we take for granted, you know, pointing it at the moon, pointing it at something like Jupiter or Saturn. And telescopes work really great for that. But anyone who's done public outreach knows there's always those people who can never quite figure out where to put their eye on the eyepiece and be able to see, especially with smaller children. When you get those smaller children and they could spend 5 frustrating minutes at the eyepiece and still see nothing, but the SeeStar lets them see it on a tablet. And we are living with a generation that is used to using tablets and used to seeing tablets. And I find for public outreach, this is an absolutely amazing tool. And it lets you share that view with multiple people and be able to, as well, if you're using it for deep sky objects, like if you point a telescope to the Orion Nebula and the person looks through it, they're going to see this sort of fuzzy, blobby area. And you're going to say, yeah, this is a really interesting nebula. And all they're going to see is like a smudge on the that needs to be cleaned off the aquarium sort of thing. But with the SeeStar, you run a SeeStar for 60 seconds on that, and you're going to start to see the shape of that nebula happening in real time, similar to a Polaroid picture developing in front of their eyes. So wonderful tool for public outreach. Now, let's talk about the pros and cons. Nothing's ever perfect, of course. So a lot of the pros, it's very portable. For when I went to Ottawa for the eclipse, it was my carry-on luggage. Simple as that. Very simple to use. Anyone can start to take images out of the box with minimal fuss. Setup time, very quick, very simple. Long battery life. You get about 6 hours of battery under normal operating temperatures. Normal being sort of like 20 degrees Celsius is what they say. But I'm out here in the prairies. I've used it as low as -30 Celsius. And at -30, doing nothing aside from just sitting it out there in my driveway, I've been able to get 3 hours of imaging on a fully charged battery. And once again, big pro is it for use in public outreach. And of course, the value. You're getting a lot of things built into there for under $700 Canadian. Cons, it's a very narrow field of view. You are not getting, it's not great for wide field objects. If you're, for example, pointing it to something like the Veil Nebula, you're not going to get, if you go to the Western Veil Nebula, pick what side you want to get. You're not going to get the whole thing there unless you shoot both sides and tile them together and mosaic them together. The other thing about the SeeStar is not upgradable. You cannot replace the camera. You can't replace the filters. You can't do anything to it internally. Now, there is a new smart telescope out there from Celestron that it gives you the ability to be able to update the camera if you want. But we're talking about a $4,500 telescope as opposed to a under $700 telescope. Once again, cons, very marginal for planets, not that great. Field rotation, as was discussed earlier, the longer you're gathering data on the image, because it's an alt-azimuth mount, the more you're going to see the rotation of the Earth, of the sky, essentially, the field rotating in there, and you're going to be even cropping tighter in your shot to be able to clean that up. And the other con is, if you really want to make it sing, if you want to get really great images, then buy PixInsight and learn PixInsight and think of the cost and think of the learning curve on that. Now, as was said earlier, I'm on Instagram, YouTube, or Facebook, just under @LivingSkyGuy. So Living Sky Guy, all one word. But also I've got my email on there, tim@timkip.com. If at any point anyone has any questions about anything, I'm really good at answering questions, and if I don't know the answer, I know I won't make up the note. If I don't know the answer, I'll help you find. We'll try to find the answer together. But definitely reach out if you ever have any questions about anything. And if you see the sort of stuff that I'm doing, yeah, like and subscribe. The same old, same old. So now let's talk about doing a live demonstration. Okay, so right now, I have under these, under wraps here is the SeeStar. So let me just get up here and I'm going to sort of walk through what's all involved if you are doing an imaging session. So first, ta-da, there we have a SeeStar. Okay, so the first thing I need to do is, I walked away too soon. I need to power it up. So there's a power button on the side. I'm going to take the headphones off for this. Okay, so I push and hold until I hear a beep. Okay, beep, beep. All right. So now it's powering up and it is getting, essentially booting up its computer. Now, the next thing I need is to launch the app. Okay, and let me just get you switch over here. Okay, whoops. Okay. Okay. So the SeeStar app is loaded into my phone, or in this case, my tablet. And while it's booting up, it's going to make some noises, and it's essentially, once it does a little bit of a grind there, I know that it's ready to go. So I push connect, and it's looking for my SeeStar, and there it is, Living Sky Guy. So I push connect, and it's going to go on there and says, do you want to join this network? And the thing about this is it's creating its own Wi-Fi network. So you do not have to use it where there's Wi-Fi. You can be in the middle of the prairies where there is no Wi-Fi, and you're just creating your own Wi-Fi network. So I say, yes, I'm going to join. So there we are, we join. And while it's connecting here, this usually takes not too long, a few seconds here. Okay, so it says, congrats, I'm now you'll notice along here around the middle, you're going to see the different things I can do. I can do stargazing, I can do solar, I can do lunar, I can do planetary, I can do scenery. So scenery, yeah, you want to use it for bird watching, that's great. It's a great way to justify the expense to your loved one who doesn't like astronomy, but maybe thinks, hey, I can use it for birding as well. You will also see things like what's today's best targets, what's happening with the moon, what's the visibility like where you are, all of that stuff. Battery power, everything ready to go. So today we're going to talk about solar imaging. So I push solar and it says install the solar filter. Okay, so the solar filter itself, let me just switch over here. Okay, so the solar filter, oh, great. The sun is coming down here. So now we've got a nice bit of flare here. So that's the solar filter that comes with it. Now I'm putting it into a device that's going to make it a lot easier for me to find the sun. And here's why. The SeeStar itself is really great at finding targets in the night sky because it uses plate solving. Essentially, it takes an image, it looks at what the stars are, and it knows exactly where it is in the sky. But when you point it to something like the moon, or you're pointing it to something like the sun, it's not using plate solving. And that's one of the, if there's a complaint about the SeeStar that people have, it's the fact that it's really bad at finding the sun. You could spend 10, 15 frustrating minutes trying to find the sun, especially with that very narrow field of view. So this little thing here, there's a lot of plans for them on the internet. If you know someone with a 3D printer or whatever, you can print them up. This particular one I got from All Star Telescope in Edmonton, and this came with a few other accessories under $6. A great little thing. Okay, so now going back to the app here. Okay, so it says I need to move the SeeStar into position where I can install the filter. So I'm going to push and hold the button here. And when we come over to the SeeStar, you're going to see the SeeStar is now moving up into position. But I don't want to point it just at the sun yet. I just want to take it that far. So I'm going to take it to about there. I'm going to stop. And now I'm going to put the filter on. Okay, and that just goes right in here. This thing also doubles as a dew shield. So at nighttime, it's going to help keep dew off your lens, even though it does have a dew heater, but will also help to keep stray light off if you are doing it in an urban environment. Okay, so I've got that in there in place. All right, now the next part gets a little trickier because I'm going to be doing this from a distance. Okay, so now what I need to do is I need to get it centered onto the sun itself. Now, if we go back to the app, okay, it says right here, just below, once you've installed the filter, it gives you an option to go installed or go to. I do not use the go to. If I use the go to button, it's going to try to find the sun, and that's when it gets really frustrating. So instead, I'm going to say skip go to and go to observe. So now I'm skipping to it, skipping go to, and now it's literally giving me a live view. So you're seeing now just this little orangey look to it. And there's a little circle here, which will now allow me to adjust the scope. And I'm just going to switch over to the scope here just to give you an idea. So you can see now I'm manually controlling the telescope. And in fact, let me just zoom in a little bit closer here. Second here. So you'll have a better idea what I'm doing. Okay. So now what I'm going to be doing is using the touch screen on my tablet. I'm now moving it up, moving the telescope up. I'm going to switch back to the scope view again here. So I'm going to be turning it in such a way where, oh, I'm going too high here. Sorry. This is where I'm going to be a little more fumbly here. Just because I practiced this earlier today, hours earlier today, when the sun was in a whole different position. So second here. Oh, there we are. We're getting warmer. Okay. And let's see. Oh, came out of the frame. Just a second. Yoink. I'm just going to shift this camera just a bit. Okay. So you can see at the front of that purple thing is the pinhole, and at the back is the light of the hole. We want that hole basically, I'm sorry, that light to go into the target in the back end. Okay. I'm sorry, I'm doing this in real time from a distance, and I'm probably going to make a few mistakes here. Oh, big mistake. I'm going to slow it down a bit, slow the speed down so it can be a little finer adjustment. Okay. Oh, we can speed it up just a bit here. This is so much easier when you're not doing it from 15 feet away. Sorry. I guess, Mick, this is the brave part you were talking about.
Always, man, but it's the blemishes that make
Come on.
real
Nope,
tool
wrong way.
clever.
Ah, there we are. Almost there. Almost there. I'm sort of looking at the screen while I'm doing this because on the screen itself, in fact, I'm going to switch you to screen mode. You're going to see as I get closer, you're going to see it get brighter. Oh, wrong direction, Tim. Come on. Oh. The reason I'm not talking is because if I did talk, I'd probably say something that they won't let on YouTube here. Just a second, we're getting warmer. Ah, Tim.
Uh-huh. Uh-huh.
Now, remember I said it takes a frustrating 10 or 15 minutes? Well, sometimes it's frustrating real. Okay, there we are. So now suddenly there it is. So you see the sun's in here. Then what I'm going to do is I'm going to push the center button here. There's a button on the side that lets me center it. Okay, so then it centers it, brings it into position. Now I need to focus. So I'm just going to touch the side here, put a little square in here, push the autofocus, and it's now go back and forth until it brings it into focus. And then boom, there we are. As you can see here, There's the scope itself, and there is the view. And now, just like any tablet, if I want to get in closer, I can just pinch and zoom, come in for some details. If I want to adjust exposure, I can go in there and I can manually adjust exposure and or gain just by simply sliding along here. So I can make adjustments or let it do it automatically. It generally does a pretty good job of automatic. And if I then go back to the full frame view, okay, so if I push the, hang on here, 1x, right now this is on the 2x setting, so it's magnifying it 2 times. Or no, I'm sorry, this is 1x, there we are. Now, if I want to bring it in tighter without using pinch and zoom, I can go 2x, and that will magnify twice as much. Or if I go 4x, 4 times as much. But the more I do that, the more I'm going to run into pixelation issues. Now, normally, if I want to image it, I can image it a number of different ways. For example, I can choose time lapse. And with time lapse, I can do anywhere from 1 second intervals up to 60-second intervals. Or I can use, if I don't want to use time lapse, I can hit the wrong button here. I can shoot a photo, just that single image. Or if I want to get a stacked image, or I just want to shoot a real-time video of it, I can just push the video button. And if I push the video button, I want to turn on RAW and then shoot my video in RAW. And the advantage of that then, normally I'll shoot about 15 to 25 seconds video. And then I'll be able to go in to the software internal in the unit and let the unit do the stacking for me. I'll export that raw image into whatever software that I normally use for editing. Primarily, because I'm doing most of this in a tablet, I'm putting it in Photoshop Express, and I use that to basically do things like adjust the clarity, adjust the texture, adjust the contrast, and the saturation until I get it looking the way I want it to look. So as you can see, it's a pretty fun little tool. It's pretty simple. It's pretty straightforward and easy to work with. And the camera that I had on my face, apparently now the battery's died. I didn't know this meeting was going to go this long, but instead I'll let you look at the SeeStar instead, or we'll just go back to the sun. But that, my friends, was a bit of my take on the SeeStar. What do I see of how this is going to fit into the future? Okay, the most important thing I see with the SeeStar is anything that gets people interested in the sky is a wonderful thing. Okay. And the nice thing about the SeeStar is, like I say, it's literally added thousands and thousands and thousands of new people out there getting involved in astrophotography. And now let's be realistic. For every 100 SeeStars that are sold, probably 60 of them after 6 months will be sitting on a shelf somewhere or be for sale on Facebook Marketplace. From the 40 that are left, maybe about 25 of those people will be happy with the results they get from the SeeStar and will happily go on using their SeeStar. And the last 15 of those 100 will say, this is really fun, this is really enjoyable, and I'd like to even get better pictures than this. And those are the people that are going to be spending the $3,200 or $3,300 on that imaging rig. And what I see here is, the nice thing about this is, if a person can get into imaging for this low of a price and realize that this is something what they want to do, they'll always have a use for the SeeStar, and then they're going to, of course, upgrade their equipment. But if you get someone who starts by spending $3,200 and realizes that this isn't what they want to do, they've now lost $3,200, and they'll get a fraction of that back by going to Astro Buy and Sell, trying to get rid of it. But anyways, as you can see, the sun is starting to move into some clouds right now. Okay, so I guess that's nature's way of telling me it's time to wrap this up, Tim. So on that happy note, I want to thank you for giving me the opportunity to spend some time with you, and clear skies.
Tim, you would make a fabulous salesman. I know that wasn't your purpose.
No.
The memory that I have is back from the late 90s when I
Mhm.
bought an ETX 90,
Mhm.
the first sort of transportable go-to telescope
Yeah, that's right. Yeah,
that
I remember those.
ever come across. It's sort of good to know that 30 odd years later, there's actually been some progress in the technology.
Mhm.
I'm going to be very curious to see what the responses are from some of our other members regarding their current modes for doing this type of imaging and what their future plans might be. So with that, I'm happy to throw it out for questions. There was one online about whether it has rotation cancelling. You made that clear. Is there anything in the audience there, Dave?
Okay, any questions? I've got the mic up here.
Well, actually, in regards to rotation cantilings, here's what's happening. There's a lot of people that are mounting them onto equatorial wedges. Okay. So, and the idea there is that it's still working as an altazimuth mount, but on an equatorial wedge. And it's eliminating the field rotation aspect of it. But the problem is there's a lot of backstage jiggery pokery you have to do to make it work. And ZWO says this was not made to go onto a wedge. And the thing about it is, if something were to fail, as in, let's say you live in an area where you're got quite a tilt, you're putting a lot of stress onto that tripod thread. And if that suddenly snaps off and you've now got a broken mess at your feet, guess what? You're on your own.
I used to live on the equator. You can imagine what the ETX with an Altaz mount had to contend with there. So,
Yeah.
Dave, do we have any questions from the audience?
I don't see any hands up here. No? No?
Okay,
No.
with that.
It's great. That was very well done. Thank you.
And,
Oh, you're very welcome.
yeah,
Thank you very much for giving me a soapbox.
And for here we are, RASC across the provincial borders, rah rah,
Absolutely.
all that.
Yeah. Oh, excuse my kitchen mess here.
Yeah, no problems.
All right.
Again,
Take
thanks,
care.
mate.
Clear skies,
Cheers.
everyone.
Okay, so Dave.
Just give me a second here, or just have
Okay.
to screen.
Okay. 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 And so we come to our observation reports, and it's back to John.
John, the clicker should be down there. Just push the big green arrow to move it forward. If it
Unless
doesn't work,
Robyn
just
stole
yell
it.
at me. There we go.
I forget what day that was taken, but it was after that big grouping. AR 3664 had already rotated around the limb, but there was still more coming out. So,
John, can I get you to use the handheld mic? We're not hearing you through that mic. Thank you. There's a switch
I'm
on
not
the
sure
side.
which
You said to
date
turn it
I
on.
actually took that, but it was probably several weeks after that big AR 3664 had rotated around the limb, but there was still plenty of spots coming there.
That mic's not on. Just hang on a second.
Okay, there's a close-up of it. It was 2 days later that the Auroras,
Try this one.
okay.
So, okay, that's better. That again is that AR 3664. That was on a Wednesday, as I recall. By Friday, it had rotated towards the limb, and about 6 hours later is when the Auroras started that big outburst we had on the 7th, I think it was. There's another grouping of sunspots. I was using it at the 4x setting, and as Tim said, it does, you lose a little bit of resolution because it gets a bit pixelated. Okay, there's M13. That was just a 2-minute exposure. That was it says 4-minute, but it actually rounds up. As I recall, it was around 3 minutes and 20 or 3 minutes and 30 seconds. That was taken just a little over a week ago when I was in the Adirondacks at an astronomy camp. And it was amazing, like 3 or 4 minutes, what sort of images you can get. And these are, again, are all from the SeeStar. That one was taken just 2 nights ago. And anybody who's tried observing the Helix Nebula, you know it's a very, very low surface brightness. So that one took 21 minutes. And even at that, you can see it's still pretty grainy. I could probably use an hour exposure for that one. But it's nice the way the colors came out, though. That's the western veil, I think it is. And that's a 10 or 11-minute exposure.
My apologies, John.
Oh, there, I was 2 different ways of processing it. That the one on the right, I cranked the saturation up to maximum, and it looks a little, to my eyes, a little garish and overdone. But if you're doing public start party or public outreach, that's probably what people want to see. So I took that image and then put it into an image processing program and dialed down the saturation. So the one on the left looks a little more natural or more like what you would see in a telescope eyepiece. And there's the other half, the witch's broom. And again, the saturation was cranked up fairly high for that one. Oh, no, okay. That's like a before and after comparison. The one on the right has the maximum saturation, and the one on the left, I dialed it down a bit. I guess it's a personal preference, what you like. The one on the left looks more natural compared to what you'd see in the eyepiece. But for people, you know, the general public probably like the one on the right better. It's more like what you'd see published in a magazine. And again, these were 10 or 11-minute exposures under a fairly dark sky, probably a Bortle 7 or 8. Or sorry, not, no, it goes the other way, Bortle 3 maybe? 3 or 4? 3, I think. This was another one that was just taken 2 nights ago, and it's a crop because that was about a 30-minute exposure. And the one on the upper left is the Deer Lick group. There's one, it's NGC 7331 is the big galaxy, and you can see a number of little galaxies around it, mostly to the left of it. And then down to the right is the famous Stephan's Quintet. And that group, I think, is something like 14th magnitude. The faintest galaxy that it actually identified was 16.1, but I think there may be stars even fainter than that. And that was from the outskirts of Ottawa. It was around a Bortle 4 sky. I guess that's it.
Thank you again, John. And now Richard, who will then be leading us into the observing challenges for the next month as well.
So Richard, please use the handheld mic because the lectern mic is not working properly.
Oops. Now that one's from last month, when one of the challenges was to actually draw the moon.
Richard, please use the handheld mic. Thank you. It should be on.
So this is
Thank
when I asked people to try and draw pictures of the moon. This is my own attempt at drawing. I was looking at it through my 8-inch Schmidt-Cassegrain telescope. And what really caught my eye was this really dark shadow towards the bottom of the drawing there. So this is one of the things that really is an advantage of doing a drawing rather than taking a photograph is you can emphasize the things that you are seeing and noticing more. And it really with a photograph. So I really encourage people to try and draw what they're seeing. And it could be the moon, it could be a planet, it could be a nebula or a star cluster. But the more you actually try and express what you're seeing, the more you will actually see as well. So it's a great technique. Now for this month, for July, I suggested people should try and observe the Milky Way. You do really have to get out of town to see the Milky Way. There's no way you're going to see very much from the center of Ottawa. Playing around with my M100 camera just on a Star Adventurer tracking mount. Nothing very fancy, nothing very expensive, but taking long exposures and stacking them up. So this is actually a stack of 20 30-second exposures. And then because in that time, the Earth rotated, of course, everything on the ground would be blurred as the camera is moving. But I took one of the pictures and added it in afterwards to the stack of the sky background to get the nice picture of the, that's the Rolf Meyer telescope dome there, and the trees are on the horizon. So that's my version of the Milky Way. That was the challenge for July. And here it is zoomed in a little bit more. This is just using the kit lens that came with the Canon camera. So I've zoomed from, I think it's 18 millimeters up to 45 millimeters. And now you can actually see a whole bunch of really interesting objects in the Milky Way. So I've labeled them here. We've got quite a number of Messier objects. Down at the bottom, just above the spout of the Sagittarius teapot is M8, the Lagoon Nebula, and then above that is M20, the Trifid Nebula. So those are really beautiful objects to zoom in on. But then the big one that was also the next level challenge was M24, the little Sagittarius star cloud. And then all around it, there are other clusters and nebulas as well. So lots and lots of targets to aim at in the Milky Way. Right up at the very top, unfortunately, it's hiding behind that screen sharing label. Can we get rid of that? Yes, there it is. Okay, right at the very, very top is M11, just very close to the Scutum star cloud. I'm not getting, oh, there we go. Oh, no, I've gone too far. There we go. So zooming on M11, this is in a different night, a few nights earlier from my backyard in Ottawa. And the star clusters cut through the light pollution very well. So this is no problem to capture from Ottawa. Got this lovely little cluster of stars, M11. It's also called the Wild Ducks cluster, though I have never been able to see much of wild ducks in that.
And then this is a combination of both the binocular challenge and the level 4 challenge, because right across diagonally from the, right across the diagonal here is the star cloud of M24. It actually fills the entire field of view, which means you're seeing a lot of little stars in there, but you can't see that it's a cloud because there's no outline to it. But you are seeing that there are a few less stars up in this area and trees down here. Oh, well. That is the M24 star cloud. And within it is another little open cluster. So right there is a denser portion of stars, and that is NGC 6603. On the opposite end of the spectrum, there are two little areas here which seem to be depleted in stars. And those are some of the dark dust clouds that are blocking the stars of the Milky Way. So this area of the sky is a really great binocular target. You can see a lot of different things going on here. So that's my versions of all of the July challenge objects. So those were the challenges there. Unfortunately, I didn't manage to get a picture of Mercury or Venus in the twilight. Other people did. In fact, quite a few people posted pictures or observation reports from the star party last month, and they were seeing both Mercury and Venus. We also had a few other pictures of the Milky Way. Andrea and Oscar both posted pictures in advance. And Mark Lilienthal, Adam Bell, Greta Bradley all saw Mercury and Venus at the star party. Tony Jarrett had a nice picture of M24, also from downtown Ottawa. And then I started seeing some pictures coming in of the people on holiday. So Eric Toussignan posted a picture of the Milky Way over Rideau Lakes. I have a couple more myself. I've been out at Georgian Bay, and I hope I've captured a good picture of the Milky Way from there. So for the next month, for August, we're going to go a little bit farther to the east now, and not in the Milky Way, but the water constellations are starting to come up now. And of course, the primary water constellation is Aquarius, the water pourer. It's a kind of dim constellation. It's very large, but it's going to be a bit of a challenge for people to find it. So I think this is what you should be looking for this month. Look underneath the head of Pegasus. Pegasus is fairly easy to spot because there's a big square in the sky. If you look under the head, you'll see a little array of 4 stars right here, which is known as the water jar. From a very dark sky, you can definitely see them with your naked eye. I did just the other night. In binoculars, you should be able to see them from Ottawa. And then the interesting thing to see from there, trail your binoculars farther down towards the horizon, and you'll see a whole bunch of pairs of stars. I wouldn't call them exactly double stars because they're not that close together, but there's definitely pairs of stars with similar brightnesses here and here in particular. So there's a kind of trail of them. That's the stream of water spilling out of the water jar. So that's your binocular challenge. Then if you want to do some astrophotography, the Helix Nebula is a great target. It's a lovely planetary nebula. It's very large and it shows up beautifully in photographs, but you do have to take long exposures to catch anything there at all. You won't really be able to see it with your eye unless you're using quite a very big telescope. Now, the one other reason that I chose Aquarius as our challenge constellation this month is that it's bracketed on either side by the Saturn Nebula and Saturn itself. So those are the two other challenges. The Saturn Nebula is about the same size in the sky in appearance as Saturn itself. But of course, it's a planetary nebula, so it's much, much dimmer. So that will be very difficult. Long exposures, high magnification will be necessary for that one. So those are the deep sky challenges. And the solar system challenge is Saturn itself. Now, this particular picture I took last year, and the rings of Saturn were tilted quite a bit more. But this year, the rings are going almost flat with respect to our point of view. So there'll be just a thin, thin band. That will make them perhaps less beautiful as the ring system goes, but it also means that the moons of Saturn are in line with the equator of Saturn, and they're going to start doing transits and shadow transits and occultations, and we'll be seeing a whole bunch of very interesting moon effects around Saturn right now. So those are the things to look for this month. And keep an eye on the blaze star. It hasn't blown up yet. Should happen sometime soon. So that's it for me. Thank you.
Beauty. Thank you, Richard. Informative and challenging, as always. So, tentative program for next month. Usual intro, Dave with the skies for Ottawa. Dave will also be giving us an update on the bylaws for RASC Ottawa that have been required due to provincial legislation being changed, and it has some impacts on how we govern ourselves, and Dave will feed us through the implications of those. Unless someone else steps up, you'll have to listen to me talk about the Wizard of Oz, David Malin, and looking for a second presenter at anyone's leisure who may wish to step forward. Observation reports, challenges, blah, blah, blah. Next one, Dave, please. Estelle is not here. She's off at the Starfest, skylarking on taxpayers' expense. So to her, next. Fred Lossing Observatory, members only star parties. Members may take guests. Next one is September the 7th, just after our next meeting. Thank you to all the RASC Ottawa doers, the movers and shakers that make things work. According to Dave and/or Chris, we got up to about 80 participants tonight, and I have to thank all of you, and all of the presenters for putting up with our technological difficulties. And also thanks to the staff of Chasm for helping out with the tech and logistics. Comments, critiques, blah, 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 to me as meeting chair at ottawa.rasc.ca, or I'm Mick Wilson on the RASC Discord server. Snacks and conversation at Liam Maguire's on Saint Laurent at sometime after the meeting for those of you that wish to attend. And with that, next meeting, Friday, September 5th, same media, same place, hoping to see you all then, and happy trails. Thank you.